it's not very necessary, but anyway. So vibration is something we encounter in daily life quite often, especially with the machines and technological devices such as trains, machines, cars, I don't know, airplanes, or music instruments, let's say. And vibrations play a role in both in, well, producing motion and also in producing sound. Sound is some production of sound is also caused by, as you know, by vibrations. So let's go on with some basic. I'm going to go with some basic concepts, but before that, some of the vibrations we deal with are useful for us, but many of them are harmful. For example, the vibratory motion of fans cause noise, or the machines cause noise. Sometimes the too much vibrations cause destruction of the whatever object you have because of resonance. You might cause wear and fatigue in the machines. So preventing those vibrations is quite important in our applications. But also there are useful, let's say, uses of vibrations. For example, a vibrating compressor that a person working on the roads might use, or you might use vibratory testing in order to find out whether a specimen has cracks or anything like that. You might use it in ultrasonic cleaning. You might use vibratory conveyors, or you might use, for example, dentist instruments, let's say, and so on. So there are certain uses of it. There are certain harmful effects, but the important thing is to understand what goes on so that you can either use it for useful purposes or eliminate the harmful vibrations. So we define vibration as any motion that repeats itself with a certain period. That is, if you have a certain motion that repeats itself with a period that just goes on forever, on and on and on, that we call vibration. For example, a typical example of that is a pendulum that is vibrating. Let me see, I guess I cannot draw it here. This, not on this PDF. Anyway, a pendulum, for example, which goes back and forth, is a vibrating device. The guitar string, or any kind of string that vibrates and produces sound, is a vibrating device. A machine with an unbalance, for example, a washing machine, is again a vibrating system, which is sort of harmful. We try to minimize those kind of vibrations if possible. Okay. Now, first of all, the essential components of vibratory systems are the following. You should have a spring or elastic element which stores potential energy, and then you should have something like a mass which stores, or inertia, which stores potential energy, which stores kinetic energy. I'm sorry. Just a second. Let me show this to you by whiteboard. Hopefully I can show it. So the basic elements is you need to have a spring K, okay, that is spring, which stores potential energy. And then you need to have a mass which moves and stores kinetic energy. These are the essential components. But on top of this kind of combination, spring and mass combined, you can have a sustained oscillation like this one. A vibration that never dies out. Okay? X versus time. But if you want a realistic thing, because there is some sort of energy dissipation or friction, so if you want something like this, something which dies out eventually, you also need a device like a damper, which we usually model by, let's say, by a viscous damper or a shock absorber like this one. So the most common elements we have are mass, spring, and damper. Again, let me share my... Okay. So mass and mass, spring, and the damper are the three essential elements. And the way vibrations happen is basically the potential energy and kinetic energy is interchanged. That is, potential energy transforms to kinetic energy, and then it transforms back to potential energy, and so on. That causes a sustained oscillation. In the meantime, if there is a energy dissipation, the energy is dissipated, and there might be some source of energy which causes the vibration. Okay. So the importance of vibration comes from the fact that the vibrations have well, harmful effects as well as useful effects. For example, if you have an automobile that has a lot of vibrations, that is quite uncomfortable. So you probably want an automobile in which the vibrations are minimized as much as possible. Okay, here I can draw things. So, on the other hand, structures such as bridges, for example, require proper design for vibrations. If you don't design them properly, because of the phenomenon called resonance, you might have failure of the structure. For example, the Tacoma Narrows Bridge, in which I put a picture over here, in 1940s, this phenomenon probably was not very well known. The bridge was designed, but then the natural frequencies of the bridge coincided with the frequency of the vortices caused by the bridge, that is caused by the wind and the bridge. So the wind induced by the vibration caused the bridge to collapse, which led people to design bridges, for example, taking this effect into account. So we designed machines such as turbines, engines, and so on, so that they don't vibrate that much. Therefore, we save. First of all, they don't have too much vibration. Plus, there are savings of energy because of undue vibrations, let's say. Okay. So we need to analyze and understand vibrations in order to eliminate them or use them for useful purposes. There are certain videos, I don't know whether we can watch them here, but I have put them here so that you can watch it. The collapse of the For example, Tacoma Narrows Bridge is here. You can watch these videos by yourself. There's a helicopter resonance video in which it is shown how the helicopter blades can enter to resonance. I might do that. I might show this video to you maybe at the end of this lecture. Okay. Now, the parameters of vibration, as I have told you, there are three essential components: spring, mass, and damper. We will be studying them in detail very soon. Actually, they will be studied in the videos I have already uploaded. In the spring, if you apply a force on a spring, it causes a displacement. If you apply a force on a damper, it causes a velocity displacement, and if you apply a force on a mass, it causes a acceleration. Okay? Now, how do we model? One of the important things we need to do is to model our systems. And the way we do it, we take a physical dynamic system, and then we develop a conceptual model for it. For example, if you have a motorcycle like this one, from this motorcycle, you generate a model such as a mass, spring, and a damper. Although this model has nothing to do with the real motorcycle, in some sense, it represents the motion of this motorcycle, let's say. From this physical model, the simplified physical model, we can draw the free body diagram and write the governing equations from the free body diagram, and using Newton laws, for example, we can derive the equation of motion for this system. Using the equation of motion, we can find out how the system will behave under certain conditions, so that we can go ahead, analyze the system, or make certain changes in its parameters so that your system behaves in a better way. Okay. So we will talk briefly about the classification of vibrations. The first classification is free and forced vibration. Free vibration is when you have vibration without any forcing. You have something like this. You pull this thing from here to another point and leave it. And then what this thing will do over time is oscillate and eventually dying out oscillations. Okay, this is free vibration. Forced vibration is you might have the same system. Let's use the proof drawing. But you force it, the f of t, and it causes a sustained oscillation, in which case the oscillation will be, it will be going on like this. This will be forced vibration. As that is one classification, we will be studying both of these. Forced vibrations are more important because we are adding energy to the system in the case of forced vibrations. You might have damped or undamped vibrations. If there is no damping, then there is no energy dissipation, and there is always the problem of resonance there. Resonance is more dangerous when you have undamped vibrations. You might have linear and nonlinear vibrations, but in this class we will just be studying linear vibrations. Nonlinear vibrations is when you have elements that are nonlinear. Those are hard to analyze, so we don't really, we won't be really dealing with that. And there is deterministic and random vibrations. We will be dealing with deterministic vibrations. We will be looking at the simpler cases. So a free vibration is the natural vibration of a system when there is no external loading, and the forced vibration is when there is a forcing that varies with time. Okay, so this is the end of this presentation.